Hello everyone and welcome back to JCE Connect. I'm Professor Rajendra Jotawar from Jain College of Engineering. In previous class we are studying about the third model of cloud computing, that is virtualization. And today we'll be studying about taxonomy of virtualization. Virtualization covers a wide range of emulation techniques that are applied to different areas of computing. A classification of these techniques helps us to better understand their characteristics and their use. The first classification discriminates against the service or entity that is being emulated. Virtualization is mainly used to emulate execution, environments, storage, and networks. Among these categories, execution virtualization constitutes the oldest, most popular, and most developed area. Therefore, it deserves major investigation and further categorization. In particular, we can divide these execution virtualization techniques into two major categories. Those are process level and system level. Process level techniques are implemented on top of an existing operating system which has full control of a hardware, whereas system level techniques are implemented directly on hardware and do not require a minimum support from an existing operating system. Within these two categories, we can list various techniques that offer the guest a different type of virtual component computation environment, like bare hardware, operating system resources, low level programming language, and application libraries. In taxonomy of virtualization, we have two major virtualization. First one is execution virtualization and other types of virtualization. Under execution virtualizations, we have machine reference model, hardware level virtualization techniques, operating system virtualization, programming language level virtualization, and application level virtualization. Whereas in the other types of virtualization, we have storage, network, and desktop virtualization along with application server virtualization. Starting with the first one, that is execution virtualization, it includes all techniques that aim to emulate an execution environment that is separate from the one hosting the virtualization layer. All these techniques concentrate their interest on providing support for the execution of programs, whether these are the operating systems or a binary specification of a program compiled against an abstract machine model or an application. Therefore, execution virtualization can be implemented directly on top of a hardware by the operating system, an application, or libraries, dynamically or statistically linked to an application image. Virtualizing an execution environment at different levels of a computing stack requires a reference model that defines the interface between the layers of abstractions, which hide the implementation's details. From this perspective, virtualization techniques actually replace one of the layers and intercept the call that are directly toward it. Therefore, a clear separation between layers specified their implementation, which only requires the emulation of an interface and a proper interaction with the underlying layer. Modern computing systems can be expressed in terms of reference model, which describes that at the bottom of the layer, the model for the hardware is expressed in terms of instruction set architecture, that is ISA, which defines the instruction set for a processor, register, memory, and interpret management. ISA is interface between the hardware and the software, and it is important to the operating systems and the developers of the application that are directly manage the underlying hardware, that is user ISA. The application binary interface, that is ABI, separates the operating system layer from the applications and libraries which are managed by the operating system. ABI covers details such as low-level data types, alignment, and call conversation, and defines a format for executable programs. Systems calls can be defined at this level. This interface allows probability of applications and libraries across operating systems that implement the same ABI. The highest level of abstraction is represented by the application programming interface, that is API, which interface applications to libraries and or the underlying operating systems. Next, we have hardware level virtualization. It's a type of technique or virtualization technique that provides an abstract execution environment in terms of computer hardware on top of which the guest operating system can be run. In this model, the guest is represented by the operating system The host is represented by the physical computer hardware, the virtual machine by the emulation, and the virtual machine manager by the hypervisor. Hypervisor is generally a program or a combination of software and hardware that allows the abstraction of an underlying physical hardware. Hardware level virtualization is also called as system virtualization, since it provides instruction set architecture to virtual machines, which is representation of hardware interface of a system. This is to differentiate it from the process virtual machines, which expose ABI to the virtual machines. Next we have is hypervisors. A fundamental element of a hardware virtualization is the hypervisor, or the hypervisor is also known as virtual machine manager or VMM. It recreates a hardware environment in which the guest operating system are installed. There are two major types of hypervisors, type 1 and type 2. Type 1 hypervisors run directly on top of hardware, therefore they take the place of an operating system and interact directly with the ISA interface exposed by the underlying hardware, and they emulate this interface in order to allow the management of operating systems. This type of hypervisors is called native virtual machines since they run natively on hardware. Type 2 hypervisors requires the support of an operating system to provide virtualization services. This means that they are programs managed by the operating systems which interact with it through the ABI and emulate the ISA of a virtual hardware for the guest operating systems. This type of hypervisor is also called as hosted virtual machines since it is hosted within the operating systems. Conceptually, a virtual machine manager is initially organized in three main modules: dispatcher, allocator, and interpreter. They coordinate their activity in order to emulate the underlying hardware. The dispatcher constitutes the entry point of a monitor and reroutes the instruction issued by the virtual machine instance to one of the two other modules. The allocator is responsible for deciding the system resources to be provided to the virtual machine. Whenever a virtual machine tries to execute an instruction that results in changing the machine resources associated with that virtual machine, the allocator is invoked by the dispatcher. The interpreter module consists of interpreter routines. These are executed whenever the virtual machine executes a privileged instruction, a trap is triggered, and the corresponding routine is executed. The design and the architecture of a virtual machine manager, together with the underlying hardware design of a host machine, determine the full realization of a hardware virtualization, where the guest operating system can be transparently executed on top of a virtual machine manager as though it were run on the underlying hardware. The criteria that need to be met by the virtual machine manager to efficiently support the virtualizations are equivalence, resource control, and efficiency. In equivalence, a guest running under the control of a virtual machine manager should exhibit the same behavior as when it is executed directly on the physical host. Under resource control, the virtual machine manager should be in complete control of a virtualized resources. And efficiency, a statistically dominant fraction of a machine instruction should be executed without intervention from a virtual machine manager. The major factor that determines whether these properties are satisfied is represented by the layout of the ISA of host running the virtual machine manager. In the next class, we will be looking at operating system virtualization, programming language level virtualization, and application level virtualization. That's all for today. Thank you.